Hi Savita, I'm just starting that session again. Okay, okay. So I'm hoping that this time there is no lag, although I haven't done much other than restarting my routers and all. Okay, great. So is there a lag still? So I'm on the mapper slide now, and now I have gone to reducer slide. Okay, great, great, great. So the problem is, you can say, the resolved. Excellent, excellent. So let me just check if people are joining, or is my mail gone correctly. Okay, a mail has gone to everybody. Okay, and something is going in the background. All right. So I was discussing about reducer. All right. So whatever we had put values in mapper during our mapper code, we had put certain values into the context. That values are taken out by Hadoop, and then they are sorted, and all the values for a particular key are grouped together and fed to reducer, one key at a time. Okay, but that does not mean the instance of this class is going to be created every time. So it creates an instance of this class once for each, for the whole input. Now it runs the reduce function again and again on each key value pairs. Okay, and here you are going to get two input things. First is your key, okay, and all the values corresponding to that key, okay, is what you're going to get in a reducer. All right, and you get a context in which you are supposed to aggregate all these values and put the value back. Okay, like this we said, context dot write and then key and the new value, this one. Okay, so all you're doing is you are going over all the values here, and then for each long writable I get the actual long value and sum it up. And once you have summed it up, again you could translate it into long writable. So any communication you do with Hadoop in numbers, you have to use their data type. Like we are using long writable here, we could have been using int writable or other things. Okay, so, but internally you do the standard long thing, and to convert back and forth between long and your primitive long writable, you can do long writable dot get. You will get the actual number, actual long, and in case you want to create a long writable, you put the value here, and that's it. Okay, these are pretty efficient data structures. Okay, these are pretty efficient data structures. Okay, now, so this is what it is, and the next steps are, you define something called a driver. Driver's job is to define what is basically tie everything together. So we created two classes. First was the mapper, second was the reducer. Now we are tying them together to make a single job. Okay, so here first we are giving it a name. Okay. And then we are basically creating the driver itself. Okay, the driver itself. This is the class here. Basically a driver is nothing but an entry point class whose job is to basically kick in the whole map reduce process. All right. So this is what it is. Okay. And there are other things like we define the output key, output value, input key, input values for the our reducer and mappers. Okay. So once we defined inside each of the mapper and reducer, and once we are defining now. Okay. And here, this is how we have defined the input directory or output directory. Okay, great. Now I will show you, where is it? So this is my Java code. I will have to increase the font size. Okay, colors and fonts. Okay, so let me see how big it is comes. No, it is not yet come. Okay, so I've just increased the font. That's it. So this is what our mapper looks like. Okay, this is my mapper, this is my reducer, and this is my driver in which we define a config for conf, and then we do all of this. And here we are adding the input path, and here we are adding the output path to the job. Okay, this is my job from top to bottom. That is one, the string of the connecting string of all the things. All right. Now, once we are done with this, okay, we click on export and then export a jar file. And right now I'm exporting everything into this one. Okay. So I say training 2, that's it, and then say finish. It is done. Now the next step is to take this. So this is my local folder, and I'm saying scp and training to jar to student at hadoop1 dot nobigdata.com, and I'm putting it into my folder, all right, called as Giri. So it has been copied. Now I go back and SSH. Control U and SSH. So this password you can avoid by setting up passwordless SSH by copying your SSH key. You can search on internet how to do a passwordless SSH. Okay. Now, so this is my folder. My folder is little too cluttered. There are too much of data here and there. And this is what we have just copied, training2.jar. All right. And now the next step is to execute it. Okay, we exported the jar, copied it, and this is the way we are going to execute this. Okay, not this one. Okay, this is the one. Okay, now here we go. We go back one step and then Hadoop jar asgiri slash training to stub driver. Stub driver is the entry point which we defined at the last moment, and these are the files where we have stored our input. This is my input folder and this is my output folder. Okay, and these are on HDFS, both these folders. So once you kick it in, you start this whole process. It will start the process. It says, now remember that it says that output directory already exists. You can see this output directory already exists, which means we might have to either delete this directory or so I'll show you that. So here I'm trying to take up the input from this folder and putting the output to this folder. Okay, let's have a look at it. How does it, not this one. I'll go to, this is my Ambari and I'll go to Hue. Okay, in Hue, the student and password is same as for your SSH. Okay, now here, if you go to the file browser, there you will see that inside the asgiri, you will see there is a word count already. And there is an input file. This is where I have put my big text file over here, and there is this output folder. Okay, from the previous run it has this output folder already, so you can delete this folder and it will be created, or you can just rename it to, okay, so I've just renamed it. Okay, so I'll just rename it to output 2 and that's it. Okay, now it's renamed. Now it will happily do the job. Okay, so as soon as a process of MapReduce starts, it gives you a tracker ID also, so that you can keep track of your jobs. And as we discussed, most of the Hadoop is basically about that job processing. So you might have to monitor what's going on. Okay, as you can see that it has reserved this much of memory, this much is used, and so yeah, we could have renamed from SSH itself, Savita, but I preferred to show it through the file browser so that I could have shown you the other folders as well. Okay, this one is from Job Tracker, Tuhin. So basically every time Job Tracker launches it, it gives you a way to monitor the whole job. Okay. So these are the nodes running. 2, 3, and 4 are my task trackers, while my Hadoop 1 is the job tracker, as you can see. So hope you guys explored. Did you guys explored both 8080? I mean Ambari as well as Hue. Did you guys explore HDFS? This is the view of the HDFS where everybody is creating their folder. You should also create your own folder over here. Okay. And then here I will be putting various kinds of data which you can process. Right now my folder contains various kinds of other data also which I'm working on. Okay. Like for example, we have movie ratings or 100,000 movie ratings. So I'm doing all of that. Okay, okay. So basically in the session one, there is an instruction manual. You should look at that instruction manual and it'll have the password and login for everybody. I don't want to tell the password here because the video getting recorded and audio getting recorded. So you should see the session one and there is an installation instruction. You should see that one and you'll get the details. Okay, great. Now, so is it still running? Let us see the nodes applications. Okay, word count is this one. Start time is there. It has succeeded already. Okay, right. And it has after it has run, it has put the data where in the Asgiri, and there is a folder called word count, and then there is a output. Okay, this is where it has put the data. Now note that in the output folder, okay, note that in the output folder, this is how it looks like. All right, so these are the words which have that many frequencies. Okay, and since we have not removed special characters, we are getting these all sorts of words. Okay, so the next exercise for you guys is to write a word count after cleaning all of these special characters. Okay, and removing commas, exclamations, and all of these, and figure out the frequencies of various words by ignoring the basic articles. All right, so this is what we got. Okay, this is what we got, and we also can see it using command line. We say Hadoop fs minus ls. It shows me my home folder. Okay, and then I say sgiri and then say word count and then output. Okay, so this shows the two files which we have there, and out of this, the part, had there been two reducers, there could have been two parts over here. Right now there is only one part. Okay, and if you have to see what is there in that file, what you can do is instead of ls you can say cat. All right, this way all of the full file going to get displayed to you. Okay, so hope you got the idea. So next, you should basically try out taking this code which I have done today, and I will also be uploading and making the whole jar available to you along with the source code so that you can experiment it and then make it work. All right. Now let us say, okay, let me just check if the recording is going on. Yeah, awesome. So basically we were able to see all the directories. Now the next point people ask is, what if your program is dependent on certain libraries which is not there in Hadoop or which is not there in all the nodes? So Hadoop has given us a nice thing called libjars. Okay, so if any variable, so it gives you a variable called libjar. So you put all the jar files, say my.jar, email.jar, this.jar, that everything a comma separated format, and export that to a variable. And when you run hadoop.jar, it will all of take all the values from libjar and put and make it available to all the nodes in the network. So this basically makes it very very simple and easy to launch your application, because any dependencies you have in your application, you put those dependencies in libjars and those jars will be made available to everybody. Earlier, when this libjar was not available earlier, what people used to do is people used to combine their product jar plus dependency jars into a single jar, and that was always very big headache. Is there any command to check name node and data node in cluster? Okay, so basically, okay, so generally you, okay, how should I say this? Basically, Hadoop status gives that. Okay, and okay, basically I need to figure that out. So far, I mean, the way we all had been using it is using Ambari for this. Okay, to see what all nodes are there. Like in this case, where is our Ambari? It shows us the first you go to the services. Okay, it shows you there are three data nodes, one name node, secondary name node has been stopped, and similarly in case of a mapper reducer, you have got four clients for map reduce. Or in case of a yarn, the terminology is little bit different. There is a resource manager instead of job job manager. Okay, it is called resource manager, and instead of saying task managers, it's called node managers. That's the only terminology differences there. So right now there are 3 by 3 node managers, which means task trackers, or job resource manager means job trackers. Okay, so there is a one resource manager, 3 by 3, all of the three task trackers are alive. Okay, so this is one way to check. Okay, and I don't know how do you check from the command line, but generally is like you can see the JPS, I mean Java processes. Okay, it's not there anyway here. Okay, and this one will also show you which service is being run where. So if you go into zookeeper service, shows you it is being run here. Okay, and these are the hosts. If you clear the filter, right now there are four hosts, 1 2 3 4, and the second one is not having the secondary name node is not yet running, which means we don't have a great failover right now. Okay, and these are the RAM memories of each one. I have kept intentionally, I've kept different RAMs for different machines, 1 GB, 1 GB, 2 GB, 4 GB. Okay, and these are the various components installed on various machines. Okay, so you can actually browse through the Ambari and you will have a very good clarity on the cluster. This is the general overview of the cluster. So network usage has suddenly gone up. Okay, because not many people were using till now. Okay, all right. So this is a good way to visualize your network and experiment a bit. Similarly, in case of HBase, HBase is also master slave kind of model, and that's pretty much it. Okay, more we will discuss when we get into details. Okay, okay, let's move on. And once you have defined all your libjars, you can pass all your libraries like this. Okay. So a comma separated list of jars, you can pass it to Hadoop, which it will make available to the whole network. So Ambari is a basically server side monitoring kind of platform, and it doesn't have Eclipse because Eclipse is your local one. Okay, so that is the reason Ambari doesn't have the Eclipse in its toolset. Ambari is basically a sort of service monitoring kind of a UI. and controlling the whole cluster. It helps you controlling the server. Okay. And yes, yes, yes. So Ambari is completely doesn't care about what programming language you use. Ambari cares about what servers are you using, what clusters, what machines, what all services are there, on what port. That's all Ambari cares about. Okay. What all clients are installed. Java matters only to the people who are writing MapReduce code. Okay. Ambari is basically a website which shows, this is the website which basically shows you the whole matrix about various servers. These are region server database performances and everything. And other than Ambari, you have Hue here. Hue's job is to make you interact with each service. It provides you HDFS browser and uh, Uzi editor, Pig editor, Hive editor. Basically, you can write your code in Hive SQL queries here. All right, right, right. Now, great. So the next step, once you are done happily with the basics of map and reduce, or even before starting launching your map and reduce, the first step ideally should be that you should create a test case first. Okay, test case plays a great role. Okay, so right now what we saw was we first wrote the code, then created a jar, uploaded it on the server, then executed, and then waited for error to occur. Okay, this whole loop is really, really big. Okay, and when you are coding or when you are building your map reduce logic, this might kill you. Okay, this will irritate you that even for slight change, I have to go through such a long cycle. Okay, that is why people came up with the test case, and then this is the reason, like people might turn to saying that we'll just use Python, and instead of launching it on real Hadoop, I can just put a sort command over there in between, right? So therefore a test cases was very necessary, and so on the similar line, a test case is created where you define a map reduce driver. Once you are done defining all of that, you define something called, basically define your input. Okay, this is the input. This is my first line. This is my second line. Sandeep Giri is here. To teach the map and reduce class is fun. So these are the two lines I've added into the input and pass that input to my reduce driver and run it. Okay, that's all. So once you are done with it, once you get the output out of MapReduce driver, you compare it. Compare and check whether it is right or wrong. Alright? Like here, if you see there is step test. Okay? In this step test, you can see clearly that we have first setup. Okay? First setup in the sense we set up a mapper, then a reducer, and then we tie them together and run it. And this basically helps the testing really, really easy. So you don't have to upload anywhere. You don't have to upload anywhere. Okay. Okay. And it will just run in the local machine itself. So you can say, not this, you can say here in the run menu, run as run as Java test. Okay. And it will run. here only. So this one has successfully completed. Rest of the things are anyway not implemented, therefore they will give error everywhere it is failed. So there are three test cases: test mapper, test reducer, and test map reduce both. So this one has succeeded. Okay, because I have not put any conditions here. Okay, so and if you see it has also created the output over here. Okay, as I was describing to you. Okay, so basically we were counting the frequencies in these lines. This is one line, this is another line, and my code has counted the frequencies and printed them onto the screen. Is 2. Okay, so instead of sending it all the way to HDFS and trying to run it, you can check your logic, test your logic on the local machine itself without making any change in your code. Okay, basically these are great testing frameworks. Same MapReduce driver, we have fed we have fed different input data. All right. So to it we have said add input, and this is what MapReduce driver, what we have done here. Okay. So if you see, we have just created a MapReduce instance here, and that's it. Okay. And this class is nothing but a class provided by the test framework, basically a mock of the actual driver. Okay, this is the mock of the actual driver. This is not really Hadoop MapReduce driver. MapReduce driver is nothing but the one who controls the execution of MapReduce, or defining both of them together. Okay, hope I did not confuse you guys too much, or did I? Okay, so basically in very nutshell, here all I'm trying to demonstrate that to test your code or the logic, all you can do is you can define your MR MR unit test case. This is called MapReduce unit test cases. And then once you're done with that, you can quickly run those things locally instead of first uploading onto the server and then running the Hadoop job, which will take too much of your time. This comes as a very very great tool. Okay. Now I'm moving on to advanced concepts. Do you have any questions right now for me? I'm muting for a second. Okay, I'm muting for a second, and I have to grab a water bottle. So first we discussed about the basics, and then we are moving on to little bit of advanced concept. This is generic. Okay. Now the only Java part we discussed was how to write map reducer in Java, how to write test cases in Java, and then I'm moving on to map reduce advanced concepts. Okay, so these are general concepts, and there might be a minor somewhere, a little bit of Java somewhere, but don't worry. Okay, so in one of the examples earlier we said that the sentence was being split over multiple machines. Okay, so those kind of advanced concepts we are going to discuss something today. Okay, So I'm going to take this example little above. Okay. So Hadoop divides input into fixed size pieces called input splits. Okay. If you remember, we were discussing something earlier about HDFS slicing the files into chunks. Okay. And those chunks are also known as splits. Okay. These are splits. Basically, they are uh, it's a not a split. It's called HDFS block, 64 MB blocks. Okay. Now the same the same block is taken up, and then we create input splits on top of HDFS blocks so that our processing of each input is meaningful. It should not be completely erratic, like half word in one split and half word in another one. Such kind of thing should not happen. Okay, that is why Hadoop came up with the concept of input splits. Input splits define that what kind of input is going to each mapper from the HDFS. Okay, because if you look at the HDFS block, it will be completely meaningless to your program. Okay, at various times. So each mapper's instance is created per input split. Okay, and each input split contains multiple records, and those records you can say that are basically on each of the record is your map is applied. All right. Now let me try to put it in different words. So there was something called SDFS block. It is basically a hard limit of 64 MB or something or similar. It's a very fixed size block. Okay. And that block need to be converted into something which is little more meaningful to your code. Okay. And that's where the translation from HDFS block to input split comes into place. Okay. Why does it make sense? I'll just move ahead and then come back. Now think about this. Think about this. Say you have got records 1, 2, 3, 4, 5. Okay. And there you hit a block boundary of HDFS. So half of this record is going to be in one block and half of this is going to be in another, right? And this will be very, very inconsistent for your application, right? You want to operate on fifth record. This fifth record has to be operated by some program. Now we just ran a word count program, for example. We were concerned about individual word or individual lines. Okay, we were not concerned about each individual byte, right, or bits. So under the hood, HDFS might be having a word on a boundary such that half of a word is existing in one file, half of the word is existing in another file, and therefore an input split is required such that this last word, is pulled from the second boundary into the first one itself. Okay, so that we can operate upon it, or we can move the fifth word into the uh, this second. Ideally, this word fifth word is moved into the second one and let the second one be operated upon here. Okay, but if you look at the block boundary from the right hand side, okay, so generally it is like this. So the moment you hit a case where your input split is being shared by two HDFS blocks. I mean, half of the input split is one side, half of the input split another one. Then that particular input split is shifted to the another node. Okay, and so on. How do you define a record? That is another objective. The way we have just defined an input split. Similarly, our code, there is a class, basically there is a Java class which does this for you. Okay. So right now, by default, we talk about the words and lines. Okay. So the default input splitter job is to it's sort of a text or word splitter whereby each word should go to a single, should not be splitted. Similarly, you can also build a similar input split which takes care of the sentences. You remember the sentences we discussed in the first problem? So you can build your input split to make sure that is each sentence is a record, a collection of sentences, or a paragraph or collection of paragraphs is one input split. And I mean, no two paragraph, no one paragraph goes to different input split, and hence it will help you in doing a lot of text analysis, right? So you can define your code to translate from HDFS block to input split. Okay, and Hadoop provides a lot of functionality to that. So you can write input split classes by extending input split in your own fashion which you wish. Like for example, like the way the default one basically does the split line by line. Okay. Each line is sort of a record, and a collection of lines is basically input split. And hence half of the line doesn't go to one mapper, and half of the line does not go to another mapper in the default input splitter. So similarly, you can make sure by extending input splitter that half of the paragraph doesn't go into one mapper, and half of the paragraph doesn't go to another one in exactly similar fashion. And you can make a sentence instead of a line for processing. Okay, so the way input is recognized by your mapper is something you can do using extending input splits. Okay, so do you have any questions regarding input split here? This is a very important concept. Okay, I missed Arun's question. Can we have different size input splits? Yes, the input split size might vary a bit. Okay, because the word which is on the boundary has to be moved. Okay. Does an input split run on name node, or it is run all across? Okay, because it has to read the block size and convert those. So it's basically a client library which is given to you. I mean, basically it's run on each different node when your code is executed, and it's a sort of a library on which your code will depend internally. How do we configure this and where? So in this code, you can see that. So where is our stub driver? Okay. So here there is something called input format class. Okay, you can define your input format class, and then you can set that as input format. So this input format class will take care of giving you the proper input size. So by default, there is a default class set for this, which takes care of, which makes sure that word does not split. So similarly, you can do that. Yes, yes, you are right, Savita. And basically, to solve our problem, we might end up creating a new kind of input split based on exactly what we are looking for. If our, if we are, doing sort of a grammar check, okay, you would want to keep a paragraph on the same mapper, okay, or you want to do some other analysis, then you might want to do some other format, right? So so your question is whether you define input split based on lines or paragraph depends on the problem you are solving. Yes, for example, in our problem we don't care about paragraph exactly, but that a line is not split across, yes. But to make sure that this doesn't happen, you will have to create your own input splitter. This is called input format class. Okay, not, I mean, a little bit different nomenclature. Input format class. So there are multiple commonly used input splitters available in case of Hadoop. Okay, so you don't have to worry too much, because if you, for the initial analysis, you will find your input formatter. There are multiple input formatters available, and I think I have listed down here. Okay, okay. Hmm. So so it means that it happens on the fly during mapr job. Could transfer not full fs chunk but only small input to other return. Yes, 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 yes. So only small, those ones which are lying on your boundary, you just inform the Hadoop framework. Basically, you means your input format class will inform the Hadoop that, hey, my boundary is finished. You can give this from this to the next guy. Okay. And that is how Hadoop figures out that where to, which one to send it to the next node and which one to keep it on the same node. Okay, great. Yeah. So basically the important ones are, first one is the word one, where we have the word, basically input. It's called text input formatter, and there are some more actually. I'm not able to recall right away. Okay, but if you have a, yes. So input splitting is done as soon as the data chunks are being read. Okay, you cannot do it alongside, because first you need to read the chunk, figure out whether the boundary is lying between the chunk or on the chunk boundary. Okay, so you'll have to do it after you finish reading it. Okay, or parallelly, basically as soon as you are reading each block, you keep on reading it and then you perform. Okay, but cannot be truly parallelized because it has to wait for the input chunk to finish. Okay, great. So this is the concept called input splits. And whenever you do a little bit of advanced processing, you end up creating your own input splits. Okay, and the input split, the signature is the length the length of the input split plus the locations of each files or each chunks on the HDFS. Okay, so that's the Java way of defining things. Great. So each input split is, you can imagine that is a bunch of lines or bunch of rows, and mapper runs on each record of input split, and you can think of record on each line or each row in database. Okay. If there are too many splits, okay, if the input split you are writing is creating too many small input splits, there is a higher overload. Okay. So therefore you need to figure out a great uh, input split size. Therefore, almost all the input splits are equivalent to HDFS block. Okay. Just that each input split need to have the full record rather than half record. So, Savita, which one do you want? So you want me to repeat what does it mean? Yeah. So in case you are defining your input split size very small as compared to HDFS block size, then you might end up creating too much of overhead. Therefore, input split need to be generally equivalent to HDFS block. And this is the Java definition of input split. This one. So each input split has got a length and a location. Location as in where all this particular data is existing. So input split is generally required for text-based data. Right. So Arun's point is that it is generally required for text-based. In case you are okay with byte by byte data, then you are happy here. You don't have to worry about much about HDFS. Okay, worry about input splits. Yes, you are right. Right. And Hadoop tries to run maps near to the data location. Okay, and this particular optimization is called data locality optimization. It tries to run your mapper code closer to data as much as possible, and this is done using data locality optimization. And in case all the nodes hosting the same replica of data, so since each of the chunk is going to get replicated, a chunk and HDFS block are the same thing. I'm using them interchangeably. So each of the HDFS block is going to be replicated on the network. So if all the nodes hosting your data on which you have to operate, or all the nodes on which my particular data on which the map is going to get executed, if that particular all those nodes along with their replica are really busy, or task tracker is down on those nodes, in those circumstances Hadoop will run the mapper near to that data, meaning all the computers which are closest, the computer which is closest to the data. Okay, and this is what we known as data locality optimization. Okay, so Hadoop's tendency is first try to execute the mapper on the computer on which your HDFS block is located. Okay, all right. So if it is not found there, if say task tracker is not running, it's not able to execute mapper on that node. In those circumstances, it will try to execute it on the same rack as in the nodes which are connected together, the computers which are connected together to a local hub, the nearest one, and then it will try to execute it. In case it doesn't work out, it will try to execute in the same data center, and then the final result is to execute it in another data center. Okay, so a common question. Okay, so Savita's question is, if the input split need to ensure paragraph or chapters, are not split, in those cases, the splits will not be equal to the size of block of variability. Exactly, exactly. So it does impact the optimization because basically the things which are lying on your boundary, you will have to transfer them across. Okay. And since the input chunk size is generally 64 MB, in case of Apache Hadoop and in case of Cloudera, it's 128 MB. It would not be much of a problem. Imagine that you are just transferring, say, a paragraph contains, say, a paragraph at most contains 100 characters, okay, or 200 characters, or say 300 characters. So 300 characters means 300 bytes. So the transfer at most you can imagine is of 300 bytes, okay, between the nodes. Okay. So Arun's question is, will we get overview of all config files in Hadoop used for setting rec config, HDFS block size, etc, etc? Okay, actually I have not planned yet, but if you want I can do that. Okay, if you want I can do that. I'll make a note of that because that is not part of the curriculum. So I'll do that. Okay, so I'll just make a note of myself. If you wish, okay, all configuration details of Hadoop. Okay. Okay. Because I mean there are too much of details in the configuration details, configuration of Hadoop. Okay. I will try to summarize it, maybe a couple of slides. All right. Now, so this is what I was trying to describe earlier, how the input split is there. Now here, this is called data locality optimization. Okay, so on this one, if you look at it, ideal case is this color is for map task, this is for HDFS block. So map task and HDFS block are executed on the same computer, same node. Okay, this is a rack. Okay, this is a rack, it has got multiple nodes, and this is a single data center. Okay, so this one is the ideal case scenario. In case, in case, I mean, this HDFS block is maybe a replica or maybe the original one or either one. Okay, in case map task is not able to execute on the same node, it will first try the same rack. This is the rack, it is trying its best to execute on the same rack as closest as possible. In case it is a data center like this, okay, and it's not able to execute the map task on the same rack, it will try its best to execute it on the same data center. Okay, and how do we define this? We will actually discuss it after some time. Okay, okay, so hmm, let me just go over one more time the input split. Okay, so here you can see that the input split is defined as the length of the input size and locations where all does this input split exist in HDFS block. It could be multiple HDFS blocks, single HDFS, it is kept very generic. Okay, and there is something called input format. Input format basically input format basically creates the records out of input split. Okay, basically it creates a record reader whose job is to give the records one by one to the map. Okay. So given an input split, this guy input format will create records for you. Okay. Input split is has the length and locations of the actual data. Largest get processed first. Okay. In case of an input split, input format creates a split. Basically, it creates records here. It creates records. Not this. I'm sorry. Okay. Okay. Input format. This one creates the records out of it, and then uh, basically this is the function which creates records. Oh, sorry. So input format does both the jobs. Okay. This is just a representation of an input split which says it has a length and it has a location. And it is the duty of input format to first split the block size into input splits, and given an input split, creating a record on top of it is the job of the input format. So if you want to do anything, if you want to change the way the inputs are broken right now, you will have to extend this class. Okay, this is an abstract class, you will have to extend it to make your own. Okay, so there is a clarification. The mapper is synced up to all node data. Why can't we pick the mapper from the next node with different data chunk instead of looking for the node that has next replica of data? No, actually, not. Okay, I did not get the question. So the mapper is synced up to all nodes data. No, basically each mapper is executed only on one piece of node data, right? Not all. It doesn't know about all. So each node, each data node is containing only a small piece of data. Okay. And so if the data, I mean, first job of the mapper is to execute the task on the same node on which the data is lying. If it is not able to execute the mapper on the same node where the data is lying, it will try to execute on the same rack. Okay. I mean, before even executing on the same rack, it will try to find out if is there any other hosting the same data? Is there any other data node hosting the same data in position and is in position to cater to mapper right now? And therefore it tries to first find the replica, and once the replica is not there, or the server on which replica is running, replica data lies, in those cases it will try to execute it on the different node. And different node, the order of priority is same rack, and then same data center, and so on. You can define the complete tree of your own choice. Input split is only for text data, or is it yeah, it is applicable for any kind of data. It is up to you how do you define it, how do you define record. Okay. All right. Now another question to you is, can reducer take the benefit of data locality optimization? Perfect. Perfect. Because reducer is going to need the data from multiple nodes, and hence and generally reducer is either one or maybe two. So the data anyway has to get transferred from one place to another. All right. So there is not much of a benefit that it can deduce from I mean from data locality. Okay. Okay. So each input split is further divided into records, as we said. A map function is applied on each record. A record is like a logical entity, like a row in case of RDBMS. An input format creates records. Okay. Now, if you have to store a file with a replication factor of 3 on which all nodes will Hadoop store this file. Okay, this is again a question about data locality. I think data locality I should move a little bit here, and this one should go up. Okay, I'm okay now. Great. So if you have to store a file with the replica factor of 3 on which all nodes Hadoop will store this file. Say you are trying to store a file onto Hadoop. Okay. So in your opinion, where should it store this file as well as its replicas? Let's say the replica factor is 3, which means it is going to have total number of 3 copies. Basically, this data will be take the thrice of the total space, actual space. 2 in the nearer node and 1 in farther. Okay. On the same rack, second copy in the same rack, third copy in the data center. Okay, okay, okay. So this is interesting. This is interesting. So the way it does it, there's a little bit of differences. Like 2 in the same data center and third in other data. So all of you are agreeing that there is a benefit of keeping the data away, at least one copy of it, right? Making it uniform. Okay. So the general tendency is to basically first one will be on the same local node, which is just either the same node or the nearby node where we are asking HDFS. So we connect to one of the nodes and say we are trying to store this, and then the tendency is to first store on the same local node, at very close by node, and then other two have to be off the rack, not even in the same rack. Okay, so that is the general tendency of Hadoop. This is to ensure the disaster recovery. I mean, this is to ensure the fault tolerance as well as the availability of our data across. Okay. 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 Now, all right. So this is how a diagram looks like when we talk about map reduced data flow with a single reducer. Okay. This is how it looks like with a single reducer. Okay. So an input file is split into say 3 sections. On each one, basically an input split is going to get created, and that input split is fed to the mapper, and mapper is going to create the key value pairs which the sort is going to take. And once the sort finishes the job, it sends it for the merging, and hence the second one, Savita. No, so 3 copies in all means replica of 3. Okay. In case of HDFS terminology, we call it replication factor. Okay. Replication factor of 3 means total 3 times. Right, right. So Arun's question is that what about what if there are more? Let me think. Let me show you the diagram once. Okay. So input is split, map was applied, sort was done. Here, then merge is happened by copying the data from each of these nodes to a central place, and then further shuffling happened. I mean, basically the group by happened here and then fed to the reducer. Reducer basically saved it to part of 0. The way I displayed in case of word count, it was stored as part dash 0. So each reducer creates a single file. All right. Okay. So basically, if there are too many reducers, the shuffling is high. Okay. If there are too few reducers, I mean, how many reducers should there be? It's a very difficult question to answer. Second, should there be mm, uh, basically multiple reducers or single reducers? That's the first question you need to answer. And the second one is, if there are multiple reducers, how are we dividing the job? How are we dividing the task? Okay. So, in case your computation is heavy, okay, in case you are doing a lot of task in reducer, then you should probably split your reducer job. Okay, but sometimes given your requirement, you just want a single reducer. That's all you want is a single reducer. In those circumstances, you cannot take the benefit of dividing the task amongst multiple reducers. Okay, this is how it happens. Can we have a replication factor more than one for a reducer job output? Let's say I want to keep copy of mr job final output for future work. Yes, 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 of course. So any output which is created by mr job is anyway going to get stored in HDFS. And if it is going to get stored and you have not tweaked the output replication factor, it is going to be 3 anyway. Therefore, therefore it is going to have the replication factor. So you don't have to worry about it. Okay. So now this is the case of having the multiple reducers. Okay. So multiple reducers is a task which is done by not combiner function. Okay, okay. Extremely sorry. Map reduce sharp is okay. Combiner functions partitioner. Combiner partitioner. Okay. So basically here we are talking about multiple reducers. Okay. Now, multiple reducers is an idea which is quite simple to do in case of normal Java MapReduce, because each reducer is given key value pairs. Okay, but in case of a streaming job, that is very little difficult to do, because a streaming job, the whole the input the streaming reducer gets is the whole input, which is sorted by the key, right? So okay, okay, I've got some question. It means, can we have replication factor parameter which is set while storing data in HDFS? Yes, and you can also configure it by default also. Okay, so multiple reducers is a parameter which you can set in the job configuration. Okay, job dot set. So I will define tell you, because before you define your reducer, you can also define basically here there is a set set number of reduced tasks. Okay, if you say 10, then it will create 10 reduced tasks. Okay, in case of Java code when you're launching it. All right, Deepak. Great. Now let me show you. So there are times when you want to shuffle in your own manner. Okay, so say you got this output, you want to divide your output from mapper to two different reducers. How do you do it? You want that all the data which is being processed for people starting with A, or people starting with less than J, should go to one reducer, while for other one it should go to the other places, or to the another reducer. For streaming, it's one, or depends on the data stored. No, it's by default for streaming it is one. In case you mark it multiple, it will create multiple reducer, but all your reducers will get a subset of the data, not the complete data. Okay, and you can also do optimization while dividing data amongst reducer, and that is why Hadoop came up with an idea called partitioner. Uh, just give me a second. Just give me a second. Sorry about the sudden break. Okay. How often do you seek multiple reducer? Can you share some real life example where it is helpful? Okay. So we'll talk about this. So as you can see this particular case, okay, what we have decided that we want to divide our data between our reducers. We realized that while we were reducing our tasks, the reducer was the one which was taking the most time. Okay, it was doing all sorts of churning on top of data. Okay, so I mean, for us, for me generally, I mean, in my case, mostly the mapper has taken most of my time, and therefore I did not had to increase number of reducer from uh, from one. There was only one time there we had experimented on increasing number of reducers, but it turned out that our mapper was basically becoming bottleneck. Okay, so I don't have right away the example in which I really increased the reducers, but frankly we never had to increase the reducers. So maybe I mean let's see this example particularly. So basically, to assist reducer, ideally either when we say increase the number of reducer, Hadoop will try to split the data equally based on certain key size. Okay. And at the later point of time, when Hadoop has gathered metrics, I mean, various kinds of, it keeps on calibrating your input execution. And once it has gathered sufficient amount of information about your map reduce job, it will keep on making your partitioner better. Okay, making the partition between reduce better. Okay, so this is the partitioner. Okay. So when you want to control which keys go to which machine and how your data is going to be balanced amongst reducers, you define a class called age partitioner, which basically partitions, which basically extend a partitioner, and this is the type of the key and value, and here it returns a number as in out of n number of partition, n number of reducer, which one goes, which one on which this particular text is going to go. Okay, so there is going to be a single partitioner execution that divides and tells us, send this data to this particular reducer. Okay, it will return the ith number of reducer, and then your key value pair will go to that particular reducer. Okay, so here we are trying to divide it based on our reducers. All right. So basically, it is based on your input data. You created something called a partitioner, which told Hadoop that that this key belongs to this reducer, this key belongs to this reducer, this key belongs to this reducer. Okay, so that is the partitioner we have. And there is a another concept called combiner. Okay, a combiner is basically, so is everybody clear about the partitioner? Do you have any questions related to partitioner? So nobody has a question related to the partitioner, right? Okay, it's always a range partition. Yeah, so basically, I mean, how should I explain this? So what do you mean by range partition? So each, right, so not really, it is completely up to you how do you define it. At the end of it, you have to tell that you send this data to this particular reducer. So reducers are named as 0 1 2 3 and so on. Okay, and if you say, if your partitioner returns a value called 0, then those key value will be sent to the zeroth reducer, and so on. Okay, it can be a word, it can be any other you think you can think of. Okay. Can we create not really, you have to, at the end of the whole process, your partitioner has to return a number. Howsoever you can do that. Okay. Howsoever you can do that. Whether using a hash, whether using an array, or whether using a number. Either way, you have to tell, you have to return as a result that this key value belongs to first reducer, second reducer, zeroth reducer, or nth reducer. So that's all. Okay, you could even come up with a scheme like sum up all the digits, all the characters ASCII value, and then divide it by total number of reducers. I mean, do a percentage total number of reducers, and hence you will randomly distribute your key value pairs. Okay, the way here we have divided it by number of tasks. Had it been say 1,000, okay, then it will, the value of this one will be somewhere between 0 to number of reduced tasks, okay, and so on, right? So we can always come up with the, okay, now here, so this is the job of a partitioner. Okay, it basically takes the input key and throws it to that particular reducer. Okay, it's basically that guy who is switching between, takes the input, picks the input from the shuffled input from the mapper, and then throws it to the reducer. Okay, but partitioner also ensures that all the values of a key, all the keys, all the key value, sorry, all the values for a key go to the same record. Okay, therefore, your partitioner will be asked only once for a key. It will not be asked again for a key. Okay. So no matter if a key is having thousands of values, it is not going to ask the same thing again to your partitioner. It can do that optimization. Okay. Now, can one task execute mapper many mappers? I mean, in case you don't have reducer, okay, your reducer doesn't do anything. In that case, yes. Or you can combine all your mappers into a single mapper and then execute those. Okay, great, great. Now there is another advanced concept called combiner. All right. So one of the problems, first problem basically, was about counting the frequencies of all the letters in our text. Okay. Now, this is an interesting idea. So think about this. In the first problem, let me just open that sheet for you. Okay. So this is the one. This one. Not this one, not this one. This one, right? So remember this. So we had to compute the frequencies of all letters. Now imagine what is going on in case of a map reducer. So each line of this text is going to be given to your mapper logic. And this mapper logic is going to spit out. It is going to spit out basically the basically 26 numbers. Okay. Against each of the letters A to Z, it is going to spit out the letters from the numbers from 0 to something, okay, each line. So mapper will take each line, convert that into character followed by the count, okay, a1 a1 b1 c1 z1 x1 and so on, and then all of this is going to get combined together on the same machine. Okay, the output of each mapper is going to get combined on the same machine and then sorted. And then once all of this is done on a single machine, it is going to get transmitted over to another machine to get merged with it. Now, do you think doing an optimization on the single machine is a good idea? Just after your mapper has finished processing the whole input on the same machine, if we are able to do certain more processing, then it will be really, really fast. Because if you are able to compute summation on this machine itself, then your transfer of data goes drastically down in this particular case specifically, where at the end of all the mapper or combining the result of all the mappers on this single machine, the it will only end up with 26 numbers. Okay, it will be only 26 numbers if you combine on the same map on the same machine. Okay, if you combine all the frequencies of letters on the same machine, you are going to have how many? 26 numbers, that's all. Right? If you don't combine that, it will be close to 64 MB, which is equivalent to saying, uh, you can roughly say 32,000 times the data size. So if we are able to combine the output on this single machine, then then we are actually reducing our data in 1,000 times, right? So that is where the role of a combiner comes into play. Is this a concept of having reducers in each of the data node? Perfect. That is something what I'm trying to explain. So you have sort of a reducer on this single machine, and there is a minor differences between the reducer and this one. Okay, I will explain to you that very, very quickly. Okay, so that is the job of a combiner. So did you get the utility of a combiner? Basically basically a combiner is going to run on each of these nodes here. Okay, and summarize and minify the data which is produced by the whole map. And remember, each map is going to process 64 MB data, and 64 MB data, if you can process it and further optimize it, it is going to add a lot of value in the optimization. And also you have distributed the job. The other role of a combiner is to distribute a job of processing in case of reducer as much as we can onto the data nodes itself, on multiple nodes instead of doing it on a single node. Okay, that is where a combiner function comes into play. Okay, there is a interesting property of a combiner function. Okay, combiner function. Okay, so combiner function is takes the same signature as reducer function. You don't have to basically you will have to implement the same class, extend the same class as we did for reducer. Okay, so there is no need of having a newer class for combiner. It has an input key value and has output key value, a key and array of values, key and array of values. That's an input and that's an output. Okay, input is key and array of values, and same is the output. No matter in there is a very good property of a combiner function. The combiner function's property is, irrespective of how many times you apply it, the results will be same. Okay, it has to be associative in nature. I'll explain to you. For example, you have got, for say Sandeep, the values are 1, 2, 3, 4, 9, 8, 11, and so on. Okay, now a combiner will be applied on any number of values in this, not necessarily on the whole values. Okay, and then whatever combiner's result is there, multiple combiners will be added together. Okay, so you can imagine the combiner on the same machine being operated first on 9, 8, 11. Let's say we are doing simply summation. Okay, so let's say combiner was given these two values first. So combiner did was summation 2 plus 3 1. Then it was given these three values. Okay, and it gave out 16. 16 summation summed up 349 together, and then it was giving two values 8 and 11, and it added them into 19, and then again same combiner is going to be applied on these three, and you will get summations, which is 38. All right. No, so my point here is irrespective of what subset of your data is going to be applied a combiner, the result is going to be the same. Now if you think about summation, if we had like summed up all of these things together in a single shot, it will still be 38. Okay, it will still be 38. So no matter in what order and in how many ways you are summing up the values, meaning where all are you applying the brackets in this expression of summation, you will get the same result. And that is the property of a combiner. Combiner should be such that no matter in what order it is applied, you should get the same results. Therefore, not all reducers can be combiners. Okay, because it is only those reducers who possess a property of applying it onto any subset, you should get the same results. For the same reason, average is not a function which can be applied, which can be applied, which can become a combiner. Okay, average is not a function which can be applied as combiner. Okay, so let me show you 1 2 3 1 2 1 6 and 9. So if you do an average of this one, okay, okay, if you do an average, the average is 5. Okay, average of these three values, average is 6, right? Now, okay, so now average is 6 of these two values, right? If you sum up these two first, do an average of these two values. So this was summation we talked about. Summation is a candidate, good candidate for combiner. I will explain to you why why is it such weird requirement of combiner this way. Okay, so why is it so? Because what mapper does is mapper I mean, what Hadoop does is Hadoop keeps on taking the output from a mapper in chunks, multiple records in chunks, and then keep on applying your combiner on top of it. So it has no predictability that how many input records from the mapper, how many key and values from the mapper are going to be combined together, and therefore and once it has combined, it will recombine them together again, recombine the results again. Okay, you can think about that tree where you have big, I mean, divide and conquer strategy. So therefore your combiner should be such that in case you are dividing and accumulating your output, your result should be right. Therefore sum is a good candidate, but average is not a good candidate. Okay, multiplication is a good candidate, but division is not. All right, so it is there is a term called associative and there is I forgot its terminology actually. It's called uh, associative, and there is one more thing. So basically, when you are churning a large data in memory, you need to divide that data even on the mapper side, and then apply your combiner to make it minify your data. All right. So that is the property of a combiner function, and that is why it has such a weird requirement of having this sort of behavior. All right. So example is min. No matter in what way are you applying min on subrecord. Like when we sort data, we divide and conquer it. In that case, either we are looking for min or max. And therefore, a min or max is a good candidate for becoming a combiner function. Summation is one, and similarly all the candidate I mean average and say rms value is a good candidate. Okay, root mean square value, or a standard distance formula. So this one. Okay, so this one is also a good candidate. Okay, no matter how you apply this, you are going to get a correct result. Is combiner paired with partitioner? Yes, it is, but they are not relevant. Both can coexist in whatever way you wish to do. Okay, so combiner is an operation which is happen on the data node where the data is existing, and partitioner happens after the shuffling has happened. Okay, after the shuffling has happened. All right, so this is what it is. So combiner actually helps us a lot in actually minifying the lot of traffic. Okay, lot of data. So as you can see in this example also, maximum of 0, 20, 10 and 25 is always going to be 25, whether you do the max of 0 and 20 once and 10 and 25 once, and then you do the max of both of these things. So okay, so therefore therefore this particular criteria where max is this and this, max means some root mean square value. Okay, rms value we call it, rms value, rms. Okay, okay. So no, root mean square value does not qualify. But the distance formula where square root of squares qualifies this criteria. Okay. Can you explain how combiner and partition will come into picture in example of alphabet count? Okay. Now I'll take this example. So now imagine the output of each mapper in case of alphabet count. Okay. So you have got A, B, and so on. Say it will be like 64, basically 30,000 lines. Okay, these will be 30,000 lines. ठीक है. This my I mean, these will be 30,000 lines. Okay, here. Now when a combiner will be applied on this, it will become 26 lines. A, B, C, and so on. Okay, and it will become 26 lines as a result of combiner. So that was the role of a combiner in case of the first problem. Okay, Now partitioner is not much required in this case, because because all your reducer has to do is uh, has to do is basically summing up. But let's say that we want an alphabet count, and say we want two reducers. We decided that we have got only two machines which can operate in parallel and are completely free, or we have got n number of machines and we our processing is really too high. In those case you can have any number of. So you decided that our reducers are n. So the logic which will go into your reducer is return, return. So whatever alphabet comes in, your key is basically an alphabet minus the ASCII code value of A, and then you say percentage your n is equal to your number of reducers. Okay, so now your this is the logic which is going to go in your partitioner. Okay, this is the logic which is going to go into your partitioner. Okay, this is your constant which you have defined. Okay, let's say you say 4. Okay, so in this case, if you have less than 26 machines, you are happy. Okay, otherwise if you have more than 26 machine, anything above 26 is going to be free. All right, so all combiner did was combine all of these values which were 3 million lines, 300,000 lines into 26 lines. Okay, and all partitioning is doing is dividing this summation of further making it very simple, such that it becomes fairly easy for reducers to churn. So creating multiple reducer, so you decided number of reducers as okay, number of reducer task as 4, and then what you did was you took the ASCII value of your key, whether Z or something, and then found out denominator here. Okay, or you can say modulus. Okay, so let's say your key is equal to what will happen in case your key is equal to Z, right? And your number of reducer is 4. Okay, so this is going to go on. So Z is say 26. So Z minus A is equal to 26. Okay, and okay, 25, and then 25 percentage 4 is going to be 1. Okay, so it will be sending all the keys uh, of Z onto the reducer number first, and reducers are named from 0 to n. Okay, and so on. So that's pretty much with respect to the partitioner. Okay, now I will also run one more example. Say uh, our key is A. Remember, our key is basically an alphabet, like here, an alphabet. Here, A minus A equals 0. And when 0 is divided by percentage, I mean modulus by 4, it leads to it leads to 0. So it will go to the 0th one, while C C will go to the third one, and so on. Okay, and in the worst case scenario where let's say D is there, okay, D is there, it is going to lead me 3, and 3 percentage 4 is 3. So you have got three machines. You have got three machines: 0, 1, 2, and 3. Okay, you have got these three machines on which the reducer will be sending the results to. Okay, make sense? No? Savita, was I able to explain? This is just an example. You can have your own way of doing things. Okay, you can have an array containing all the values from a b c d e f g should go to first one, and h I j k l m n o p q go to the second one, and so on. Okay, just for simplicity reason I have taken this kind of example. Okay, you could have a logic something like, if key is key is in between a and j, return 0. Okay, okay, so partitioner and combiner, the role of both is optimization. Partitioner help you divide your churning onto multiple reducers. Okay, because automatically identification of how many partitions need to be created and how is difficult for Hadoop. You can assist Hadoop in making partitions such that there is a uniform distribution of processing on reducer. Okay, so that is why Hadoop has come up with an option so that you can tell Hadoop that, hey, this is how I want the reducer to process data. Okay, even if we do not specify a combiner or reducer, partitioner, the output should be correct. Okay, output should be correct without any problems. Okay, and this is how you can define your combiner function in the job dot set combiner. Also, in case of a streaming job, you can set a combiner function. Now, last point we have is the map reduce topology. Okay, in the case of map reduce topology, this is the standard chart. Okay, so hey guys, in case you are okay, I can take up the network topology part in the next session. Okay, because it's already 10:30 close to. Okay, it's little too hard on you guys also. Okay, so this is a minor point which we can take up. Today's session was actually long. So feel free to work on the problems and solve those problems, and let me know in case you get stuck. Okay, feel free to explore the server also. Okay, and it will be great if you have any point and you come up with something, then feel free to ask. Okay, thank you guys, that's all for today. Okay, right now we don't have any assignment. Okay. The only thing is you need to finish your old assignment first before we move on. Finish your quiz, finish your rest of the assignment. Okay. Before we move forward. Okay. So Hugh is running on 8000 port. Ambari is running on 8080 port. Okay. On Hadoop 1. Okay, Arun. Let me have a look at your job and then we will discuss it. Okay. Feel free to drop me an email in case you get stuck, and feel free to even try out your own Hadoop box. Download that Hortonworks machine and try it out. Okay. But I'll be more happier if you try out our servers. Okay. Great. Great. And do not fiddle with anybody else's file than yours. You can look at other people's file, and remember that it's a single login, do not bother each other. Just keep a copy of all your data in case you lose it. Yeah. So I have created a Google group, Google community, and I have invited all of you, all of your email IDs. Please join it. Okay. It will be great if you guys start a thread, and I will make sure that I answer immediately, and it becomes very helpful. So rather than having these 3 hour session for QA, we'll have the whole week for QA. Okay. Wherever you get stuck, I enjoy answering people's question, and I'll make sure that I answer. Okay. Thank you very much, guys. Bye bye. Okay. All right. Bye, friends, and stay connected on that group. And feel free to ask your question. I'll answer all your questions over there.